All right, so here we are now in the last lecture of Chapter 13. Hopefully you're feeling much more comfortable about alcohols, phenols, thiols, and ethers at this point. By the end of this lecture, hopefully you feel like you could do any sort of question on the homework set or exam or any other application that you might need this material for. So now that we have a basic understanding of the alcohols, phenols, thiols, and ethers, we have their nomenclature rules, we have some physical properties. Now we're really ready to look at reactions, and in particular we'll look at the reactions of alcohols and thiols. Phenols don't tend to do as many reactions. They're stabilized by that aromatic ring. We did talk about phenols being slightly acidic, and we looked at the acid dissociation, but we'll focus mainly on the alcohols and thiols because the phenols and ethers aren't nearly as reactive. Much like the hydrocarbons, alcohols are also very good in terms of combustion reactions. So combustion reactions, as a reminder, it's the reaction of a hydrocarbon, or in this case an alcohol, with oxygen from the air to produce CO2, H2O, and energy. And you see with the combustion of the alcohols, we already have one oxygen at least in the alcohol itself. So we don't need as much outside alcohol outside oxygen when combusting an alcohol as we do with a hydrocarbon. So we see the balanced reaction there, and you'll probably notice that in most fueling stations there's ethanol, this particular alcohol that we see in this combustion reaction, added to the fuel to help with additional oxygen to minimize the amount of carbon monoxide and other oxides that might be produced aside from our ideal carbon dioxide. So ethanol is used for that purpose. It is a little more corrosive to the system, and it does actually lower the miles per gallon that you get compared with pure gasoline. But it is helpful in that it supplies some extra oxygen, and it's therefore added to most fuels in most places for that reason. All right, so we had basically the combustion reactions for the alkanes, then we had addition reactions for the alkenes or alkynes. Now we've got a new type of reaction, a dehydration. So dehydration of an alcohol happens when you heat the alcohol with an acid catalyst, some source of H plus protons. It occurs with the loss of H and OH, right? It's dehydration, so we're removing water. So the H and the OH have to be on adjacent carbon atoms to form that water. So we see again our good friend ethanol here, the simplest alcohol that can participate in this dehydration reaction because we can't do it with methanol. We don't have adjacent carbon atoms when there's only one carbon in the structure. So ethanol is our simplest alcohol that can do this, and if you look at the reaction, we take that ethanol, we heat it with an acid catalyst, and we make an alkene. So this is one way we can form an alkene, and therefore it's a very helpful and useful reaction. So now we can take an alcohol from chapter 13 and we can make an alkene from chapter 12. So a nice way to bridge the content in the lecture material. Obviously the co-product there is the water molecule, and that's why we call this a dehydration reaction. Okay, we have here another Eastern European name for me to butcher, Zaitsev's rule, and that's very similar to Markovnikov's rule, where we said that the species that had more hydrogens is going to get another hydrogen. Well, in this case, according to Zaitsev's rule, the dehydration of a secondary alcohol favors the product in which hydrogen is removed from the carbon atom in the chain with the smaller number of hydrogens to begin with. So Markovnikov's rule is sort of those that have get, and now Zaitsev's rule is those that have little will lose even what they have. So there we see 2-butanol in the presence of heat and that acid catalyst forms almost exclusively 2-butene, where we take that hydrogen from the CH2 neighbor, carbon number 3 there in the butanol, but some of the time, about 10% of the time, we do indeed take it from that terminal carbon number 1 that has the CH3. So it's not exclusively making 2-butene, but 2-butene is your major product and just a little bit of 1-butene. So SASF's rules not without exception, but it does help you to predict the majority product. All right, so let's pause here for a learning check. We're starting to get into some heavy duty stuff, so let's just go ahead and make sure we understand the basics. So this learning check asks that you write the equations for the reactions when 2-propanol undergoes first A, combustion, and then second B, dehydration. So go ahead and please write those reactions for both the combustion of 2-propanol and then the dehydration of 2-propanol. And once you've done that, please start the video back up to check your work, but right now you'll pause here so you can complete those reactions. Good luck. Okay, so as a reminder, we have the structure of 2-propanol, which has the molecular formula C3H8O, and this happens to be connected according to that condensed structural formula with the OH group on the second carbon. So it is a secondary alcohol because that carbon that bears the OH is bonded to 2 other carbons. So for combustion, we can just use that overall molecular formula. It doesn't matter the particular layout because we're combusting it completely in oxygen. And if you did that correctly, you took the 2-propanol, C3H8O, combined it with dioxygen, dimolecular oxygen from the air in order to make CO2 and water vapor. And then when you do your balancing, you should end up with a mole ratio of 2 moles of the 2-propanol plus 9 moles of O2 gas yields 6 moles of CO2 gas plus 8 moles of H2O gas. For the dehydration, because it is a secondary alcohol, you might think that SASF's rule would apply, but fortunately it is indeed a symmetrical secondary alcohol, so either way that you form the product, you end up with that same product. There's no way to make anything but 1 propene, and we don't even call it 1 propene necessarily because there is no 2-propene, right? So there we have our final product, and we don't have to worry about the majority product versus the minority product because there's only that 1 product in this case, as well as, of course, the water, which is a separate co-product. So hopefully that went well for you. If you're still struggling, it is our first foray into at least the dehydration reactions, and certainly please do try some other ones and reach out to me if necessary. Another reaction that alcohols can undergo is ether formation. So we looked at the dehydration of alcohols to form alkenes previously. Now, if we have conditions just right, if they're slightly lower in temperature, we still need that acid catalyst, but if we have a lower temperature, what happens instead is rather than remove the H and OH from neighboring carbons, we'll have those OH groups of the alcohols from 2 neighboring alcohol molecules come together and dehydrate to form an ether and water. And in particular, in this case where we have methanol, methanol can't undergo the dehydration to form an alkene because it has just the 1 carbon in its structure. So here with methanol, we really only have the option of forming ethers. In anything like ethanol or beyond, then we have to consider what's more likely to occur, and I would certainly try to be very clear about what way I would like you to lead, whether it's the formation of ethers or whether it's the dehydration to form the alkenes, because either way it's technically a dehydration, but you get very different products. Now, if you think back to your first semester general organic biochemistry course, I'm almost certain, and I'm definitely certain if you had it with me, that you came across the terms oxidation and reduction. So for organic chemistry, when we talk about oxidation, although our generic definition of oxidation as a loss of electrons or a gain in the positive oxidation state number from the equivalent of the first semester course, it still holds, but in organic chemistry, ordinarily, it's easier to think about oxygen and hydrogen. So in an oxidation, there's an increase in the number of carbon-oxygen bonds and or a loss in the number of carbon-hydrogen bonds. Or oxygen-hydrogen bonds, as we're talking about the alcohols here. In the reduction of an organic compound, there's either a decrease in the number of CO bonds and or a gain in the number of hydrogens. So that's how we tend to view oxidation and reduction in the context of organic chemistry. So hopefully that'll make it a little easier if you're used to the more generic Leo says GERS type loss of electrons is oxidation, gain of electrons is reduction definition that you got from your general part of your general organic biochemistry sequence. Here we see sort of a map to oxidation and reduction. So if we think back to chapter 11 where we started the course with alkanes, alkanes have no bonds to oxygen. So if we want to oxidize an alkane, we could think about oxidizing it to something like an alcohol, which has one carbon-oxygen bond. If we think about the alcohol going in the reverse direction to form an alkane, well, now we've decreased the number of carbon-oxygen bonds, eliminated the one that we had, and we also increased the number of carbon-hydrogen bonds, right? We went from a CH2 with a bond to an OH to a CH3. So we've removed one CO bond and we've added one CH bond. So we've fit both definitions there. Then if we go further to the right on that top row, we could oxidize that alcohol further to an aldehyde, which would now have two bonds to oxygen from that same carbon and one fewer bond to hydrogen. If we go in reverse, if we take that aldehyde and reduce it, we could reduce it to an alcohol where now it's gained back another carbon-hydrogen bond and lost a carbon-oxygen bond. Finally, we could go even further with oxidation in the forward direction to form a carboxylic acid, which now has 3 bonds to oxygen, no bonds to hydrogen on that carbon that has the carbonyl. So that's as oxidized as we really can get on that particular carbon. If we took that carboxylic acid and reduced it, we could certainly go back to the aldehyde where we'd have now one less carbon-oxygen bond, one more carbon-hydrogen bond, because that OH group to the right would be replaced by a CH bond. If we look down below, we could also think about the case where we're looking at an alkane that leads ultimately to a secondary alcohol in the first oxidation step. So we're looking at that center carbon of our 3-carbon chain, and we've taken a CH2 group and replaced it with a COH-CH group there in the alcohol. Obviously, we can go backwards and reduce that alcohol back to an alkane, or we could go in the forward direction and oxidize it even further to a ketone, which now has 2 CO bonds. Happens to be a double bond, but it does count as 2 bonds to oxygen as opposed to the 1 bond to oxygen in the secondary alcohol. Unfortunately, because the carbonyl carbon is surrounded by carbon-carbon bonding, we can't oxidize a ketone further to a carboxylic acid under normal conditions, all right, in our course anyway. If you go on to advanced organic chemistry, you'll see very harsh conditions that can do it, but we're going to avoid that for our purposes. So take-home message, an alcohol is more oxidized than an alkane, an aldehyde or a ketone is more oxidized than an alcohol, and a carboxylic acid is more oxidized than an aldehyde, and ultimately the most oxidized functional group we'll see in this course. Obviously, the most oxidized a carbon species can get is all the way up to carbon dioxide, and then that's no longer an organic compound. But in terms of the compounds we'll see, it's basically chapter 11, the alkanes, up to chapter 13, oxidize that one time to an alcohol. Then we can oxidize that alcohol up to an aldehyde, which is upcoming in chapter 14, and then finally oxidize the aldehyde up to a carboxylic acid, which will happen later on in the course. All right, and if we're talking about secondary alcohols, then they go to ketones, which is also part of the next chapter on aldehydes and ketones. Okay, so we just talked through that hopefully not too complicated scheme on the previous slide. Let's break it down a little. Let's talk about a single step. So primary alcohols can be oxidized to form aldehydes, and so there we see it, primary alcohol in the presence of some oxidizing agent. We tend to be very generic in our course. If you were to take the full year organic chemistry or advanced organic chemistry, certainly you'd see a specific oxidizing agent like potassium permanganate or chromic acid or something like that. But here we just have the generic O in brackets, which means some oxidizing agent that's strong enough to accomplish that oxidation. So a primary alcohol can oxidize to an aldehyde in a single step. We see, in particular, if we look at a specific compound, ethanol or ethyl alcohol by its common name, if we oxidize that particular species, we get ethanal or acid aldehyde by its common name. Don't worry, the naming on aldehydes is coming up in the next chapter, but just to see the structure at this stage is important. Obviously, a water molecule would be your co-product. Now, if on the other hand we took a secondary alcohol and we oxidized it, rather than getting an aldehyde like we do with primary alcohols, we would get a ketone. And so we see our generic scheme, secondary alcohol, an arrow with an O in brackets above to indicate an oxidation process, and then our final product would fall into the class of ketone functional groups. So we see specifically if we take 2-propanol or isopropanol as it's commonly known, oxidize it, we get 2-propanone, which is the IUPAC name for dimethylketone, or more commonly known as acetone, as our ketone product, and then also a water molecule as a co-product. So again, we'll deal with the details of ketone nomenclature, although as you probably noticed, it's not too bad. We take the OL from the alcohol and replace it with an ONE for the ketone. Now, I'm not here to trick you, although sometimes I do ask some tricky questions. So here's the first example of a tricky type question, and that would concern the oxidation of tertiary alcohols. Tertiary alcohols, because of that steric hindrance, they do not readily oxidize. So tertiary alcohol, if we were to show the same sort of thing, the arrow with the O in brackets above it, that's actually a no reaction. Specialized conditions, advanced organic chemistry, maybe, but here in our course, if you see this sort of setup, it's I hate to say a trick, but it's a question that's aimed at really getting at your understanding of the fact that tertiary alcohols do not readily oxidize. So if I gave you a specific example here, like 2-methyl-2-propanol, we would not see any product form because they would not undergo oxidation with common oxidizing agents. So if you look there, there's no H on that COH bond to oxidize. So it would be very tough to remove the methyl group in order to accomplish that oxidation to a ketone or some other oxidized form, so we don't commonly see it happen. Okay, it also involves some steric hindrance there because we're starting to get larger groups with a tertiary alcohol, and that OH group can be a little harder to react. Okay, so let's pause here for a learning check. In this case, you're going to match the products with the reaction of 1-propanol. So here we have reaction 1. The conditions are H plus and heat. Reaction 2, it's an oxidizing agent. And then reaction 3 is oxygen gas and heat. And so decide from the conditions for reactions 1, 2, and 3 whether products A, B, and C go with 1, 2, or 3. Pause the video here while you make that determination. Start us back up when you're ready to check your work. Good luck. Okay, so hopefully things look good here. For reaction 1, we gave the conditions of H plus and heat. I didn't give specific temperature here. If I did have an answer choice that was an ether, we did talk about ethers being products at lower temperature, acid catalyzed dehydration, and alkenes at higher temperature. If I wanted you to go the ether route, I would have a temperature like 130. If I wanted you to go to the alkene formation route, as we did this time, I would have given a temperature well above 130, maybe something like 180 degrees Celsius. But in this case, it didn't matter because you didn't have an ether possibility. You only had the alkene, so therefore A, the 1-propene, or just plain old propene, since you can't have a 2-propene, right? So propene is our product. For 2, the oxidation of that 1-propanol, we have now propanaldehyde, or something that you'll learn how to name in the next chapter, since you probably didn't know that yet. So there we have it. That's the chemical structure, and that you should have been able to determine based on our brief discussion of oxidation reactions. finally, O2 and heat, that should clue you in that it's a combustion type reaction, and therefore your ultimate products should be CO2 and H2O. We didn't balance the reaction to get specific mole ratios, but obviously those would be the final products in some balanced amount. So hopefully that went well for you. If not, of course, please do try some additional practice, and ultimately reach out to me, but hopefully it went relatively well for you. Okay, so now let's talk about a specific biochemical reaction, the oxidation of ethanol in the body. So one of the reasons we can consume ethanol and why we shouldn't consume any significant amounts of methanol or isopropanol or those other alcohols is that in the body, ethanol itself is oxidized by enzymes in the liver. So we get an aldehyde product here, acetaldehyde, that impairs coordination, gives those characteristic associations of drunken behavior. That's due to that acetaldehyde that you form as a byproduct of ethyl alcohol oxidation, and then ultimately that acetaldehyde is fully oxidized to acetic acid, and then even further possibly oxidized to carbon dioxide and water. So it's that preliminary reaction where the ethyl alcohol is oxidized by those liver enzymes to acetaldehyde that give the characteristic physical attributes of being drunk. If you don't drink very much and there's not enough acetaldehyde, you don't tend to get that impaired coordination. But once you've had that threshold amount, then you're not going to be making good decisions. You're not going to be able to exercise good coordination, and certainly you shouldn't be doing activities like driving or operating machinery that require good coordination. So while we're on the subject, ethanol acts as a depressant. It slows body function down as it's being oxidized there in the liver. It directly or indirectly kills or disables more people than any other drug. It's the most commonly abused drug in American society. Again, a drug is a chemical substance that has a biological effect but it's not needed by the body, and there are some people who never consume ethanol their whole lives. That doesn't put them at any disadvantage, probably puts them at a lot of advantages, in my opinion, but it's a drug because it's not necessary for us to live, but it does have a biological effect. Ethanol is metabolized at a rate of 12 to 15 milligrams per deciliter per hour by a social drinker. And again, you see that range there. That has a lot to do with whether it's a male or a female, the weight of the male or female, how much they've had to drink, what type of alcohol they've had to drink, that sort of thing. So that's why we have to give a range there. And then finally, it's metabolized at a rate of 30 milligrams per deciliter per hour by an alcoholic. So much faster rate of metabolism by someone who's used to consuming large quantities of the substance. And so therefore they need to drink more to get that same drunken effect that they are likely after. So there's some key things about ethanol, since we did bring it up in the last slide, and hopefully it's something that if you do choose to enjoy it, you do so in a social environment and certainly not in a problem drinking type fashion. And if that does characterize your drinking, then certainly I would hope you could seek some help on that. Okay, so we've looked at a lot of different reactions that alcohols can undergo. They're very versatile compounds. We did mention the phenols because they're directly connected to the aromatic ring. Those hydroxyl groups are not as reactive. They do have greater acidity, and we looked at the acid dissociation of the phenols, and that was our main reaction there. The ethers, again, we looked at reactions that form ethers when we had the two alcohols reacting at relatively lower temperature in an acid catalyst, but the ethers themselves are pretty stable. There's not much in our course that we talk about in terms of reactions of ethers. So our last discussion here for chapter 13 is the oxidation of thiols. So thiols, remember the SH group, those undergo oxidation to form disulfide bonds, and those disulfide bonds are going to be very important when we get back to discussing thiols in the context of amino acids and proteins. Cysteine is an amino acid with an R group that involves a thiol, and cysteine can form disulfide bridges with a cysteine residue later on in that same protein. So it's a very important concept. We'll establish it here where we first mentioned thiols in chapter 13, but it's going to come back very important later on in the course when we talk about the amino acids and proteins. So here we see a generic reaction. Notice we have those two thiols. This is just methane thiol reacting with another molecule of methane thiol. Above the arrow, notice, very important, we have an oxidizing agent. We have some source of oxygen because in our products we're going to get the disulfide, but we're losing those two hydrogen atoms. And in order to have those two hydrogens have a new home, we're going to need an oxygen from that oxidizing agent to make some water. So we take our two thiols, we react them together to form a disulfide bridge or disulfide bond, and we also make a water because we've used an oxidizing agent to cause this reaction to occur. And so here we see that again with a discussion of a little real-world context. So the protein in hair in particular is cross-linked by those disulfide bonds. And as I said, that occurs when you have two amino acid residues. They don't have to be neighbors. Actually, they can't be neighbors because you don't get a big enough distance. They just need to occur in such a way that when the protein folds back on itself, you get those cysteine residues close enough to each other and provide that gentle oxidation to allow for the disulfide bond to form. It's also called a disulfide bridge. You'll see that language a lot more when we talk about amino acids and proteins. An application of this, anyone who's had a PERM, short for permanent wave, they've gone through this process. It's actually fairly harsh, and you know, if you don't really need that, you should probably avoid it, but some people feel like it's necessary and worth it. But what it involves is first having a reducing substance used to do the opposite reaction. So you reduce the disulfide back to those thiols, and then you follow that with an oxidizing agent to form new disulfide bonds. So the hair has its original disulfide bonds broken and new disulfide bonds formed to try to keep it in this more desired curly type arrangement. It's still around the curlers. You have that new new disulfide bonds formed to try to hold that. Obviously it doesn't last forever, and people do need to get their perms every couple of months or even more frequently depending on how much wear and tear there is on that hair. So there we go, a real-world application of all of this oxidation of thiols and even reduction of thiols content. Okay, so before we leave this chapter, let's have one last learning check. In this learning check, you're going to select the product from the oxidation of this substance here on our left, and you're going to decide whether the product is A, B, C, or D. And once you've made your determinations, you can start us back up and see how you did. But for now, go ahead and stop the video, make your selection. Good luck. Okay, so if you notice, we're taking a secondary alcohol and we're oxidizing it, and therefore the product that we expect is a ketone. And so therefore, hopefully you noticed that, and you selected answer choice B, which would be the only ketone from our answer choices, and the only real answer that made much sense. C, I guess, carbon dioxide and water, that would be an oxidation, but that's a combustion reaction. Here we're not looking for full combustion, or we would have said heat and O2. Here we're looking for just a simple, relatively gentle oxidation. All right, so hopefully if you did miss that, it makes more sense now. Hopefully you didn't miss it. Everything's making lots of sense, and you're ready to move on to our next chapter on aldehydes and ketones. I'll see you there.